Section 7.1, inverse variation, starts off with 4 vocabulary terms. The first two aren't explicitly stated as vocabulary terms, but they do come up. Direct variation and constant of proportionality. A direct variation equation, or direct variation happens when two quantities, x and y, show direct variation, or I guess I'm using direct variation. They show direct variation when y is equal to ax. Okay? That a term, the constant value in that equation, that is what's called the constant of proportionality, the constant value of the ratio of two proportional values. That is the a term. Now we're not going to focus on direct variation a whole lot in this section, really just the next couple of examples, and that's going to be it. The main subject of section 7.1 is inverse variation. Inverse variation says two variables, x and y, show inverse variation when y is equal to a over x. Notice that x is in the denominator, and then your a, in this case it's called the constant of variation, that's the number in the top, the numerator, okay? The constant value in the inverse equation. So that is, we can say that's a in our inverse variation equation. So first set of examples, it's going to say, tell whether x and y show direct variation, inverse variation, or neither. So if it's direct variation, it's going to be y equals ax. Whatever the number is for a, it's going to be y equals ax. If it's inverse variation, it's going to be y equals a over x. And if it's neither, then obviously it's going to be neither of those two. So to determine if it's direct or inverse, what we need to do is we need to have the equation set equal to y. We need to have y by itself. Okay, so for this first example, y is not by itself, so we have xy, meaning x times y is equal to 5. So to get y by itself, what we need to do is divide both sides by x. So the x's will cancel on the left, so I'm left with y equals, that's going to give me 5 over x. Now clearly, you can see that this matches the inverse variation form. Okay, it's definitely not 5x, it's 5 over x. So this right here is inverse variation. Inverse variation. Okay, let's try another one. Number 2, y equals x minus 4. Now this one is already solved for y. We do not need to do anything to get y by itself. So all we need to do is ask ourselves, does it match the direct variation equation? Well, no, there's not a number in front of x. Well, I guess there is, it's 1, but there's this minus 4. But direct variation doesn't have the minus or plus anything on the end. It definitely doesn't match inverse variation. There's no fraction here. So it's not direct variation, it's not inverse variation. This one here is neither. It is not direct, nor is it inverse variation. Let's try a third one here. Y over 2 is equal to x. Right now, y is not by itself, so we need to get y by itself before we can make our determination whether it's direct, inverse, or neither. So we got right now, as it stands, it says y over 2 means y divided by 2. So the opposite of dividing, or how we undo dividing, is we need to multiply. We're going to multiply both sides by 2. So the 2's will cancel over there. I got y is equal to, well, x times 2, usually we write that as 2x. Now, this looks an awful lot like direct variation, y equals 2x. There's nothing on the end. There's not a plus 6 out here or anything like that. It's just simply y is equal to 2x. What that tells me, or what that is then, that is a direct variation example. That's a direct variation equation. X and y show direct variation. Okay, so if we're given an equation, or if we're given a relation between x and y like this with these 3 examples, it's pretty easy to tell whether it's inverse, neither, or direct. Okay, but what if you're not given an equation? What if you're just given data? Like in the table here, I've got just an ordered bunch of ordered pairs, x's and y's. Okay, so if it says tell whether x and y show direct, inverse, or no variation, how do we find it? Well, here's our steps. First thing we need to do, we need to find x, y, and we need to find y over x. Okay, if it's direct variation, y over x will always be the same. Okay, if it's inverse variation, x, y will all be the same. Never will you have y over x and x, y be the same for all pairs of data. Maybe one, but definitely not more than one. Okay, so what we need to do, we need to take our data, we need to make a second table. We're going to do x, y. We're also going to do y over x. Okay, y over x. So x, y, we have got 4 pairs of data, so we're going to have 4 entries in our table. So x, y, take our x term times our y term. 2 times negative 12, that would be negative 24. 4 times negative 6, that's also negative 24. 6 times negative 4 is negative 24. And 8 times negative 3 is also negative 24. Okay, so we do x times y, and we got negative 24 every time. That's very convenient. Okay, so now we move to y over x, and it's always y over x. So we're going to take negative 12 divided by 2, and that gives us negative 6. When we do negative 6 divided by negative 4, that's negative 1.5. Negative 1.5. Negative 4 divided by positive 6, we could write that as a fraction, negative 2/3. And negative 3 over 8, if you want to write that as a fraction, well, it's just negative 3 over 8. That would be negative 0.375 if you want a fraction, or sorry, a decimal. Okay, so we found xy, we found y over x. If it's direct variation, y over x will always be the same. If we look at our y over x's, negative 6, negative 1.5, negative 2/3, negative 3/8, we can clearly see that these are not the same. So these right here, not the same. Okay, but what we do see is that our xy, our product every time, negative 24, negative 24, negative 24, negative 24, these are always the same. Okay, so for this relation, for this set of data, we've got xy always the same. So if it's xy is always the same, that tells us that is an inverse relation. So this is inverse variation. Inverse variation. Okay, let's try another one here. Number 2, we got 1, 2, 3, 4 for our x's, 2, 4, 8, 16 for our y's. We need to figure out xy, and we need to figure out y over x. We'll have xy, we'll have y over x, and we have 4 pairs of data, so we're going to have 4 entries in our table. So xy, so we're going to find the product first. 1 times 2, we'll do this in purple. 2 times 1 is 2. Moving on, 2 times 4 is 8. 3 times 8 is 24. 4 times 16, that would be 64. So clearly we can see that these are not the same. Okay, so we can probably, if we go back to our directions, xy will all be the same. If it's inverse variation, well, it's not the same. These were not the same, not even close. 2, 8, 24, 64, not even close to being the same. So it's not going to be inverse variation. Now we need to find y over x. Okay, so I'll do that in green. So we take y divided by x, 2 divided by 1, that is 2. Moving on, 4 divided by 2 is also 2. 3 divided by 8 is, not 3 divided by 8, 8 divided by 3, that's what we'll just leave it as 8/3. And then 16 divided by 4, that's 4. So, we got close. We had 2 and then 2, but then we didn't have the same again. So this also, the y over x is not the same. Okay, so we knew that xy was not the same. We also know now that y over x, whoops, that should have been below that, y over x is also not the same. So if it's not the same on either line, what we can say then, there is no variation. Okay, it's not inverse, it's not direct. There is no ratio that's the same, so it's neither direct nor inverse variation. All right, moving on. New example. The variables x and y vary inversely. Write an equation that relates x and y, then find y for the given x value. So it tells you that x and y vary inversely. That's important because that tells us we're going to be using the equation y equals a over x. That's going to be the basic function that we're going to be starting with. What we're going to be given, obviously, if you look at the example, we're going to be given x and y. What we're going to need to find is a. Okay. Then we'll come back to this x equals -2 because that's going to be the second part. Okay, so let's start in green. We're going to write an equation that relates x and y. So we start with y equals a over x, the inverse variation function. We know that the y value is 4. We don't know the a value. We know the x value is 2. Okay, this is just a one-step equation to solve for a because that's really what we need to know. We need to find this a value so we can write our equation. To get rid of the 2 on the bottom, we need to multiply both sides by 2. Put a 2 out there. 4 times 2 is 8, so we can say that a is equal to 8. So what that means, let me write this up here, that our equation y equals our a value, which is 8 over x. That is the first part. Okay, write an equation that relates x and y. We've done that. Now the second part says then find y for the given x value. So the second part, they're going to give you the x value, x equals -2. Go ahead and plug that into your equation and figure out what your y value is. So we got y equals 8 over our x value of -2. This is real simple. 8 over -2, that would be -4. Okay, so it says find the y value. We've done that. Let's try another one here. Y equals 5 when x equals 4. I've got a stray green mark there. And then x equals 2. So we've got to find the equation that relates x and y first. So we're going to start back in green. We're going to have y equals a over x. The equation gives us y. It also gives us x. The only thing it doesn't give us is a. So we're going to plug in what we know. We know the y value is 5. We don't know the a value, and we know the x value is 4. Okay? We need to find a. So to get rid of the 4 on the denominator, we need to multiply both sides by 4. 4 times 5 is 20, so that's equal to a. So then what we can say is that y is equal to 20 over x. Pretty simple. Okay, moving on. Second part says x equals 2. So now we need to find the y value. So take this 2, put it right there for x. So we'll have y equals 20 over 2, and then 20 divided by 2 is 10. Section 7.1 is kind of an introductory section to inverse functions or rational functions. Rational meaning fractions. We're going to be dealing with a lot of equations and functions in Chapter 7 where your x is going to be in the denominator. Okay, so this is a basic introduction to those types of functions. As we get deeper into the chapter, it does get a little more complex, but it's basically the same idea. We've got x in the denominator, and we're going to be doing different things with it. So let's finish this section up with a story problem. The time t in hours it takes a group of volunteers to build a playground varies inversely with the number n of volunteers. It takes a group of 10 volunteers 8 hours to build the playground. Part 1. Write an inverse variation equation to model the scenario. Okay, so normally, we think y equals a over x, but we're not given y and x. In this story problem, we're given t, and we're also given n. Okay, which one is which? Well, do we choose the number of volunteers, or do we choose how long it takes those volunteers to build the playground? What we choose is the number of volunteers. Whoops. So the n value, that's going to be your x, and then your t value, that's the dependent variable. That's what is determined by the number of volunteers. Okay, so when we have our equation, really it's going to be not y. It's going to be t is equal to a over n. Okay, that's important because it also tells us it takes 10 volunteers 8 hours. So it does give us enough that we needed a t, we needed an n. Now we can find our a value. Okay, so let's do that. Okay, so our t value and the amount of time is 8 hours is equal to a over, let's see, we had 10 volunteers. Okay, so we have 8 equals a over 10. We need to figure out what a is. We're going to do that by multiplying both sides by 10 because we want to get a by itself. 10 times 8 is 80 is equal to a. So then we can write our final answer. I'll do that here in red. We're going to go with t is equal to 80 over n. Okay, so there's our equation for number 1. Number 2, how long would it take 15 volunteers to build the playground? And then 20, 25, and 30. So we're going to have 4 answers here because we're looking for 4 different scenarios. What if 15 people show up? What if 20 people show up, 25 or 30? Okay, and those times are going to depend on how many people are there. But we're going to use this function here, t equals 80 over n, to figure that out. And I'm just going to do this in a table. Okay, we'll do this in blue here. So we're going to have n, and then we're going to have t. Okay, and I'm going to leave a couple of lines in your second row, probably 3, and then that should be enough. Okay, so for the first n value, we're going to have 15 people there, and then the second number was 20, and then 25, and then 30. Okay, so we got 4 different questions to answer. We can use the same function every time. Okay, so we'll say, so we have t is equal to 80 over n. N this time is 15. 80 divided by 15, if you type that in your calculator and you can simplify this, that would give you, let's see, that would be 16 over 3, which is roughly, well, not roughly, it's 5 1/3. And then 5 1/3 is 5 hours and 20 minutes. Okay, that's getting pretty exact. If you want to leave it as 16 over 3, 16/3 hours, I'm okay with that. If you want to just make it 5 1/3, I'm okay with that too. If you can recognize that 1/3 of an hour is 20 minutes, I'm good with that as well. I'm going to leave this a little bit up to you. If you want to put it as a decimal, that's fine as well. Okay, so for 20 people, this one will be a little easier. We get 80 over 20. This one is pretty easy. 80 divided by 20 is 4. So it'll take 20 people 4 hours to build that playground. Okay, for 25, same function, 80 over 25. If you simplify this one, let's see, it should be 16 over 5 this time. 16 over 5 is, let's see, that's 3 1/5. 3 1/5. 3 1/5 would be 3 hours, and 1/5 of an hour is 12 minutes. Take 16 divided by 5, and that gives you 12, so that's where 12 minutes comes from. And then we'll have one more. 30 people, t is equal to, we got 80 over 30. The zeros we can drop, so we could have t is equal to 8/3. That would be 2 2/3. 2 2/3. If you put that into normal time, that's 2 hours and 40 minutes. Okay, so you can see that as the number of people increase, 15, 20, 25, 30, the amount of time, so if we had 10 people in the original setup, it would take them 8 hours. If by adding 15 people, or 5 people, we shave nearly 3 hours off our time. Adding 5 more takes another, hour and 20 off. Adding another 5 more takes another, 45 minutes, almost 48 minutes off. And as we add another 5 people, we're losing another 32 minutes. Okay. So the question for the final one here: what happens to the amount of time it takes to build the playground as the number of volunteers increases? I think it's pretty plain to see. As more people help, build the playground. As more people help build the playground, the less time it takes. The time needed to complete the playground decreases. And that should make sense. The more people you have to do something, the faster you're going to get it done. So, and we can see that again, like I said, in the table, as we increase the number of people, as we go from 15 to 20 to 25 to 30, the amount of time needed to build this playground declines. The more people you add, the less amount of time you're taking off every time, but you are decreasing it still. If I wanted to say how many people would it take for this to be done in an hour, hopefully you could see that if we took 80 over 80, that would give us 1, so we would need 80 people. That's kind of a side note, but just something to keep in mind as well.